floor is yours. You can go ahead.
All right, good afternoon, everyone. This is my PhD preliminary exams, and thanks everyone for coming, including my committee members. All right, to ensure that the data get deleted from your SSD, a lot of people decided to go with smashing. It's the destruction technique, such as smashing, shredding, and burning. But these techniques are not very environmental friendly in the sense that you cannot reuse the drive again. And it's not energy efficient because burning it, you need high temperature to get rid of everything. So according to National Standard Institute of Technology, or NIST, they proposed the sanitization practice into three different categories: clear, purge, and destroy. The method that I showed in the previous slides are mostly from destroys. If you want to make sure that your data is protected, people would go with destroy. But clear and purge, it will have lower level of data protections. Clear and purge, the main difference from clear and purge and destroy is you can reuse the drive in clear and purge. Clear will be more like a non-sensitive information, so you can perform something like zero overwrite onto your drive, or factory resets, or block erase. Purge, on the other hand, it will be a little bit more advanced technique. For example, cryptographic erase, secure block erase, and degaussing. And crypto, I want to highlight it a little bit here now. Cryptographic erase is for the self-encrypted drive, where you have the hardware that encrypt the data, encrypt and decrypt the data. Cryptographic erase would just delete the key. The data still remain in the drive. The key is just deleted. On zero overwrites, it's basically you have the data, but then you write everything to R0. The data disappear, but then still it's still in the program state, basically. So in this presentation, I will be focusing on two topics: the R0 override, which is completed, and then the block erase, which is the ongoing work.
So I'm going to ask about something you said earlier. Destroying, you said, was not good for the environment, right? But ultimately, these drives do have pretty limited lifetime, so they will reach the end of life. Even if you don't destroy them, they're basically practically unusable. So what do you do with them if not destroy them after that?
Actually, some companies still reuse it within the company, and some people, they don't know that the drive reached the end of lifetime. They still put it for sale on.
Okay, yeah. So those cases where it's like not reached its end of lifetime, sure. But I'm just wondering, is there like any interesting approach beyond like the actual sort of end of life where the cells have degraded so much that they're, the ECC cannot really correct anything, right? So you will at that point, how do you sort of deal with these drives? You will have to still destroy them, right? So it's either destroy them later or sooner. You will at the end of the day still have to destroy them. Okay. So, but if you're saying that you can sort of, in cases where we have not reached end of life, we can still kind of do something useful with these techniques. Okay.
But in my personal, I would rather go with the destroy option.
Okay. I have one comment and one question. So the comment is that actually Dell recommends that you incinerate SSDs at 1000 Fahrenheit to safely delete it.
Yes.
Okay. But my question is different. So why do you say cryptographic erase is not as secure as destroy?
Because in the self-encrypted drive, you basically have the data encrypted still in the drive. So, cryptographic erase is just deleting the key, not the data in the drive.
Right.
That means if you can recover the key, you can understand what the data is.
That key, I keep it separately. It's not available. So I'm thinking that you'll be sanitizing a drive for disposal purposes in somewhere. Somebody else will be using it, right? So I do not share the key. I keep it, somewhere, in a very secure manner. So why is it not as secure as destroy?
The thief still can try to get the key, can try to like reverse engineer and get the key, in my opinion, because the data is still there. The one thing you need to know is to find out the key. But destroy, it's gonna take longer time, more energy, more effort to put all the stuff together. For example, you melt the SSD at 1,600 degrees Celsius. It is almost like 100% that you cannot get anything. But for the cryptographic erase, you only have one problem: you get the key and then you get everything. So it's less of the data level protection.
It is also secure, but not many drives or not many systems has cryptographic hardware to do that, because most of this NAND storage is cost driven, right? So that's why not many drives or SD card has that feature.
But yeah, because you're talking about full drive
Yeah,
encryption.
those kind of.
All right, let's take a look at the threat model on my first work. Why Auth0 sanitization is needed. Let's say you hit the delete button, delete the data on your computer, and you think that the information is gone, but in reality, it's only logical address that get deleted, but the data still remain in the SSD on the NAND flash memory. So what would happen if someone stole your NAND flash or SSD, they still can retrieve information back. This is why Auth0 override can protect your secure information. It's just in case someone stole it, it's not going to be easy for them to get the information. And the second one, the threat model for the second work would be the data recovery is still possible after block erase. So later on, I will show everyone that even if you perform block erase at the end of life SSD and resell it on the eBay, we still can somehow recover information. And a lot of people think that block erase is already secure, but it's not. This is the outline for my today's talk. I'm going to go over the overview of NAND flash SSD, and then I will talk about the first completed work, Page-Overwrite sanitization, and then data recovery, and then conclude the talk. Before we go into the detail, let's take a look at the flash-based SSD. They are the important components are controller and flash memory chips. Flash memory chips will take care of the storing the information only. The controller will be the brain of the SSD. Will know nothing, just store the data. Within the controller, there is a software running on the controller called Flash Translation Layer, and this software will do fancy things like address mapping, error correction, garbage collections, and wear leveling to make sure that your drive reach the end of lifetime at the same times and make sure that the error doesn't go beyond correction code, the correction capability. So let's say we want to save something into SSD. The controller will be the translator that keep tracking of the host language to the physical address. Basically, the controller will keep track of the logical address and the physical address, because in reality, the data will not remain in the same physical address all the time, because controller will do a lot of management, moving the data around. So physical address will be changed all the time. So this is why the controller will just have another job, keep tracking of all the logical and physical address. Let's say we want to program something. The problem with NAND flash is programming will be on the page by page level, which means you can program page by page. But then when you want to delete the information, you have to do the block level in delete. And this would be the mismatch between the block erase and the page program. So this will cause a lot of issue in the future. And I will talk about it in the next slides. So in place update is not allowed flash because erase before write constraint. And let's take a look at why instant erase is not possible in SSD. Let's say you want to delete page 0, data in page 0. And I just want to make it clear here that when you hit delete information on page 0, it's not the actual SSD, the data is not deleted in SSD. The actual block erase will happen during the garbage collection, which means you would never know when it's going to happen because controller will be the one that decide. So you would never know. And then the data can stay in your SSD for 10 years, 5 years, or as long as you want. And the garbage collection will start when you have less of the available space, let's say 10% of available space. Garbage collection will start to happen. And let's take a look at if a case where I want to delete page 0 while you have other pages, excuse me, valid. So first, the controller will move all of the valid page into a new blocks, and then perform block erase into these old blocks, and then page 0 will be news and ready for incoming data again. So can you imagine having only one page that's invalid in 1,000 blocks in your SSD? How overhead, how large, it's going to take a lot of overhead, it's going to take a lot of time, a lot of energy. So instead, the SSD will unlink the physical page and then update the physical address. So yes, so it's gonna take a long time, a lot of effort for block erase. So instead, if you want to immediately erase information, you can program all 0. So you have your data is basically 0 and 1 bit. So you can make everything program all 0. And that's another way to destroy information. Let's take a break and take a look at the cartoon 3D NAND flash structure. Within the 3D NAND flash chips, there will be thousands of flash blocks. This is a single flash memory blocks. There are multiple subblocks into flash memory blocks. Here, this is subblock 1, 2, 3, and 4. And this is the schematic circuit diagram of a single physical subblock. This is a single flash memory cells. When all the cells are connected together in the same row, they will connect it through word line, and that will form one flash page. And now, if you take a look at the pipe, all the cells, they are all connected to the same substrate, which means when you apply the high voltage into the substrate to perform erase operations, all the cells will get erased at the same time. So this is the main constraint. This is a cross-sectional cut of the 3D NAND flash cells. The reason why I show you this, because later on it's going to be a lot of cross-sectional cut explaining physics inside the flash memory cells. So when the cells, as you can see, the yellow area, I use it to represent the storage layer, and then the oxide will be make the storage layer isolated. When you program electrons into the storage layer, that means the cell is programmed. But when you remove electron from the storage layer, the cell will be erased. And there's a difference between erase and program cells. Erase cells will have lower threshold voltage, so it will be more like on the left-hand side, and then the program cells will be will have a high threshold voltage, so it will be on the a little bit upper right-hand side. And the logics are different. Erase state will be in logic with the logic 1, and the program state will be in logic 0. The way we tell the difference between erase state and program state is using the reference voltage. The reference voltage will stay in the middle, and then all the cells that go, below the reference voltage, it will be conducting, and that's how you tell the difference between the two cells.
So where do you apply this reference voltage?
Because you want to sense
Which part in the cell you will apply this reference voltage?
what part in the cell? The control gate?
Source, then gate.
The gate. The control gate. Let's move to the first completed work, Page-Overwrite sanitization in 3D NAND flash. As I mentioned earlier, to quickly remove page 0 information, so no one can steal your device and extract information out of it, we can perform all 0 overwrite sanitization. And this work has been done, it has been known for a while. It has been done through the old technology to the SLC NAND. But in our work, we performed the all 0 overwrite on 3D NAND. And we found out that because of the 3D NAND structure, there will be some disturbance happening. And later on, we come up with a mechanism called pulse to reduce the disturbance. And then we extend this work to the TLC and see how it works on the TLC. And this is the publications we have for this topic. And before I go into the 3D NAND, let's take a look at why 2D NAND is different than 3D NAND. So the 2D NAND is basically a planar structure, and the cells lay side by side on the planar structure. It's like you're living in the house outside the country. So when you perform overwrite on one page in 3D NAND, for some college kids on the way in the back. So when you live in the neighborhood and then you have a party, your neighbor, the left and the right-hand side of your house will get interrupted, right? So that's what interferences that happen in 2D NAND. But these interferences that disturb in 2D, it's manageable. It's still below the error correction code. That's why it's not a big problem in 2D. But when it comes down to 3D, so basically you stack cells on top of each other. It's if you can think about it, it's you moving to Denver and live in the apartment on Denver, and one of your neighbor has a party. So the whole floor will get interrupted. This is something similar when you perform overwrite sanitization on one page in one subblock. everyone that share the same word line or other pages that send the same word line will get the direct disturb. And that disturb is not manageable by ECC. And this is my experimental setup. We interface raw flash memory chips using the FTDI mini model. And the socket is used to hold the chips. And by having the direct access into the raw memory cells, we can bypass the error collection code or other fancy things that controller can do. So to understand the disturbance on the last block on the disturbance from the override sanitization, we first program the full block with informations, and then we start to perform override sanitization on one subblock. All pages become all zero invalid, and then we read the last subblock to see the disturbance. And to understand the worst case scenario that the disturbance can happen, we keep sanitizing the next subblock 1, 2, 3, and 4, and then keep reading the last subblock. So the last subblock we can add the valid data, and then at this point we can see how bad the corruption would happen. And since we're dealing with valid data and also or zero override information, there are two key measurements that I use here. The first one is the sanitization efficiency. So basically, sanitization efficiency will be the something that quantify how close to all zero the override pages are. And raw bit error rate will be used to quantify how valid data get interrupted.
So the controller typically has a randomizer as well, right? So the randomizer does change the values of all of the things that are stored. Are you still using the randomizer, or are you not?
On the chips we're using, they specifically write down that there's no randomizer. So the user has to do randomizer.
Because having the randomizer, I mean, maybe it won't change much, but randomization does change the actual vector or the bit vectors, right? In essence. So in many SSDs, it does end up being used, right? And so in those cases, do you think it's gonna not be any the conclusions you have here, which you will present, I assume, they won't change, or do you think they'll change
with the randomizer on the SSD? Because the SSD is the internal controller, so I think it won't change the physics of it, the physics of the cells. I don't think it will change much basically, because if it's randomizer from outside, that would be a problem in my opinion.
Why so? I mean, it doesn't matter whether it's in the FTL or even before the FTL. Bottom line is, all that matters is that the values in those pages are going to be a little bit different, right?
Mm-hmm.
The question I'm asking is, does that matter, or the disturbance matters? Probably not, is what I would think, but I just wanted to ask you. What do you think?
So let me think about the randomizers again. So randomizer basically will randomize your information before you store it in the flash memory. To perform all zero override, you basically make all the cells into program state. So I don't think it's actually matter, because you are pushing everything into the program state anyway.
Would it sort of change the RVR values that you get, because I mean, whether you have zeros or ones is going to be important in terms of the interference.
It might flip the bit from 0 to 1. It depends on how you decode it.
Yeah.
So I don't. But I still don't think that it will matter much.
Okay, so just last thing I'll say is that the interference is a function of, when you do this all zero sort of in place override, it's a function of the values in the neighboring cells also, right?
Mm-hmm.
And the randomizer changes that, right? And so if there is some, I mean, of course, if there's degenerate patterns, all ones, all zeros, it's pretty easy to see. Randomizer will change that. So I guess at a system level, it's important to also think about, in the presence of these sort of randomizer functions, are your conclusions pretty much the same within 5% or something like that? That would be useful, right? Useful information for anybody who wants to use this in commodity SSDs, which will have those randomizers.
Mm-hmm.
So that's all. Yeah, go ahead.
Thank you for that idea. All right, let's take a look at the results and the proposed solutions. First, I want to show that this is the sanitization evaluation on 3 floating gate SLC NAND flash memory. And here we use Tesla image to represent the invalid data. And after we perform all zero sanitization. So overwrite the Tesla image into all zero with all zero data pattern. We found out that we can achieve 100% efficiency. So our image go all black. So Tesla can be all gone. And how, on the other hand, Mona Lisa image will be kept at the last block of the flash memory blocks. And as we sanitize the enabling subblock, Mona Lisa image start to get corrupted. And after you reach almost the end, like subblock 10, for example, this chip has 11 subblock. So when you reach subblock 10, Mona Lisa image, can get up to 4% of the data. And the bottom plots are the plots of the threshold voltage distribution of the Mona Lisa image before and during each subblock's override sanitization. And here, this is the straight line here. It's the reference voltage that you apply to sense the cells. And the errors come from erase cells get programmed. That's why the upper tails cross the VREF and controller will see these cells as the error.
So is this on a new SSD or an aged SSD?
The new SSD, the fresh one, yes. So floating gate, it's a big no-no for all zero override sanitization.
And with sort of aging, does this get worse?
It should get worse.
Did you
Worse.
test it?
I did not test.
Okay, no,
Yes,
that's
yes,
fine.
yeah.
Are your slides automatically going?
Yeah.
Yeah, the beginning, it's,
Here's the timing button on her PowerPoint. If we
I don't
just
know how to
unlock that, it'll be fine. But
because we later on we evaluate all 64 layer of the block within the block, and we found out that when we perform all zero sanitization on the memory blocks, you have to be careful because some layer are more prone to the error. For example, in the middle area. So when we perform all zero sanitization on this area, so have to be pay extreme precautions. And again, if you can see the hum, these are two hum. These tools are the reflect of the two-tier process. It is the process that the manufacturing used to make a flash. So instead of making all 64 layer together, they start making the upper deck and the lower deck. For example, in this chip, there are 64 layer total. So they start making etching the first 32 layer, and then do another half, and then stack them all together. And this is why we see the hum shape.
so sorry, are you trying to explain why there is that little dip in between those?
Yes.
Peak or peak?
The hum.
A peak, two peaks. Yeah, the dip is the anomaly, right?
Yeah.
I guess peaks also, but I guess the dip is also pretty straight. Right.
So are those page SLC or is there all TLC?
TLC.
Oh, but the site title is SLC.
Oh, sorry, SLC. SLC.
The message also says the video TSLC.
Sorry. It is
Okay,
SLC.
but anyway, so yeah, so why is this? Can you, sorry, please, maybe I missed that, but why is there like almost no bit errors on layers, I don't know, 28 to 32?
Personally, I think these word lines are a dummy word line. And then sometimes when you have like at the connections area, they don't use those word lines.
So if you don't use them, then why, I mean, and you're still getting the error from them, what does that mean? Are they like sort of constant values that just don't get changed?
You're talking about the bottom,
Yeah,
the zero, close
yeah,
to zero?
Yeah.
I think there could be something else on
Well,
that all
figure
zero.
out what's going on. That's very anomalous.
Yeah.
If your conjecture is that the middle layers are more susceptible, of course, we are seeing that, to, as we move towards the middle from both sides. However, this is very anomalous, right? So it would be useful to figure out why.
It might be the manufacturer is giving more margin between erase and program state because they know that these are problematic layers, so they are more precautionary step to keep more margin between erase and program.
And that's the same trend at the end as well, for the layers 58 to 62 or whatever too, right? So why this kind of interesting?
What is the key message that you want to give a system integrator from this evaluation?
So if you want to perform also override sanitization, you have to actually consider where the page add in the 64 layer. And if you do the middle area, you have to be more careful, be able to sanitize all 10 subblock. It might stop at maybe 1 or 2 subblock. And then I think at the end, the reason why it dip out like that is because of the pre-charge voltage can come in and raise the to make sure that the eraser don't get over programmed, because it's closer to the pre-charge voltage.
So the limit for ECC is 0.1% of the month, right? So looking at this figure, it seems like override sanitization is really only useful for very limited overwriting. After like SB0 or even SB1, we're starting to see things that are uncorrectable errors, right? So, okay.
This is why we come up with Pulse Solutions. It's a partial update, low disturbance sanitization engine. So basically, this is the, let me show you the cartoon of how Pulse works. This is the ready BC pin that would come up from the flash memory chips. When flash memory chips doing any type of operation, program, read, or erased, the ready BC pin will go down to tell the controller that I'm busy, don't do anything yet. So let's say 800 microsecond, we get a full program on one page. Pulse would prematurely terminate the program operations by sending the reset command. If you can see here that maybe after 400 microsecond delay, we send the reset command into the ready BC pin, and then that will stop the programming immediately.
Can I ask something here?
Yeah.
And what was your mechanism to do the override before this?
All full program.
Full
program,
okay.
yeah.
So you were indeed using full program. And,
Yeah.
Okay.
That's why we see the high disturb.
Okay.
Yes. And this is the cartoon show the the expectation of the pulse with the partial program operation, that the when we partial program page 2 on subblock 0 with make it all 0, the other pages within the same word line but different subblocks will get less of a disturb. So this is just like a cartoon to show that this is the expectation. And this is the algorithm. First, we identify what page need to be sanitized, meaning that it become invalid. And then we estimate the partial program time. And then we initialize the page buffer with all 0 pattern for SLC, for example, because we want to move everything to all 0. And then we start to perform sanitization on invalid page based on the time delay that we estimate at the beginning. First, we would issue the NAND program command. Then this is the hex value that I use for talking to NAND flash memory. And then after applying a time delay of, for example, TPP, we immediately send the reset command, and that reset command is FF. And then we use the read operation to quantify the sanitization efficiency and the RB of the valid data. If the sanitization efficiency and the RB of the valid data below the threshold, we keep increasing the TPP and then repeating step 1 to 5. Otherwise, we stop. So the beta and gamma depends on the designer to choose, and it is a constant value. So in our work, we choose the beta to be around 90% sanitization efficiency, and gamma would be 0.1% because this is the standard ECC error collection.
So sorry, what does that mean? 90% efficiency? What does that mean?
So 90% of all the bits get corrupted to get moved to 0, get programmed.
10% are still not necessarily touched, or you don't know.
Yeah, not necessary. Yes.
And so, sorry,
Yes.
I guess I'm missing the rationale of, I'm forgetting, right?
Yes.
So you keep repeating this, if your bit error rate is less than a threshold, you keep repeating it. Why?
Or because you're not, let's say if your bit, that means you still can keep going. Let's say your beta.
Increase the efficiency.
Yeah,
Okay,
yeah.
Now, can you do this on any SSD? I mean, because you are really now trying to sort of write on an already written page without any block erase, which is this a mechanism that can be supported on any SSD? Pulse.
That is a good question. Because we only performed this experiment on the a couple of flash memory chips, so it's not.
But so at least what, 2 manufacturers? Okay, but that's still pretty good that you're able to do this on 2 real chips.
Yeah. YMTC and Micron. Yes. And then this is how the Pulse will be implemented. It will be put into the controller. And then because Pulse, it's only software modification, we don't need hardware modification at all. And let's take a look at the pulse on the 3D SLC floating gate. So the left y-axis is the sanitization efficiency of invalid page, and I'll compare it with RVR of the valid page. And the x-axis is the time delay in microsecond that I put into the during the pulse operation. And if you can see here at around close to 300 microseconds, nothing happened to both images. But then we want to sanitize the Tesla image. So as I increase the TPP, the partial program time, Tesla image start to go to all zero overwrite, even though you still see some sort of previous information, but still the Mona Lisa image barely get corrupted at this point. So we can keep going. So as we keep going, Tesla image get even more corrupted in the sense that it become even more close to all zero, while the Tesla image, Mona Lisa image still remain correctable by ECC. And as we move to the full program pulse, 800 microsecond, if you can see here that the Tesla will be 100%, close to 100% sanitization efficiency, but Mona Lisa image get severely corrupted. So we don't want to get into this point. So pulse will actually stop around, for me, 550 microsecond would be the best case, but then it's still, you are risking to flip the, causing the flipping point. So yes, with the 3D SLC floating gate, we prove that the pulse can help reduce disturbance on the valid page while making sure that the invalid data get also sanitized.
So at this 550 TPP value, there is errors in that Mona Lisa image, but they're correctable.
Yes, yes, yes. It's not visible either. Yes. And then we later on evaluate the pulse and normal sanitization on 3D TLC floating gates because TLC triple level cells have different storage type, unlike SLC, single level cell 0 and 1. TLC, you are using 3 bit per cell. So these are the possibility of the states that we will have L0 to L7. And I use the Tesla, Mona Lisa, and Einstein image to represent 3 different data from 3 different pages. And to remove all 3 images together, we perform also sanitization by moving all the cells to L7 states. So
was there any work of sanitizing TLC before your work?
There's few work that working on sanitizing only SLC page, CSB page, MSB page, and then some people would talk about moving everything together. So there are some paper that was talking about like, the sanitization on the TLC in more detail. But yes, so if you take a look at the logic here in L7 state, so different company will have different logic encoding. So if you look at this L7 state, you see that the LSB bit at the L7 will be 0, CSB and MSB bit will be 1, 1, which means when you move all the cells to L7, you should expect to get some image, the image like this, all 0, all black on LSB page, all 1 in CSB and MSB page. And if you can see here that all 3 images are gone.
Figure out this encoding to get that 110.
That is going to be another paper coming up.
Okay.
So can we make all 0, all 3 pages?
We can, but then it will be some expose some data.
How can we make all 0?
Because you program all pages with 0 pattern.
So you cannot move down, right? From L7, you cannot.
I know. Yes. But then you can move up.
So all 3, all 0 is not possible.
Yes, that one is true. Yeah, with the sanitization, also sanitization. All right, and this is the pulse real evaluation on TLC floating gate. So since we are dealing with invalid page and valid page and invalid page, we have 2 sets of information. If you can see, start to check the invalid pages after after normal sanitization, all images are gone. On the other hand, if you look at the valid pages, after normal sanitization, Leonardo, Queen Elizabeth, and Michael Jackson got highly corrupted. However, with the pulse partial program, the valid pages information still remain close to the original image. The only issue is the pulse sanitization may not be able to move may not be able to make everything as the invalid page. I mean, everything as like a perfect, like a normal sanitization. And we further evaluate pulse on 64 layer. And as you can see here that the blue line pulse significantly reduced the RBER caused by normal sanitization. And this could be a promising technique for 3D NAND in the future to perform oxygen sanitization.
But with CSV and MSV, you are getting pretty high RPR for at least some layers. So as long as you're okay with losing some data,
So yeah.
right?
And this is the summarize of the other chips. We done some evaluation on 3 different chips, 3 different technology, and different mode, SLC and TLC, and we found out that pulse could be fairly useful for 64-layer floating gate because let's say in SLC mode, the error can drop down from 0.93% to 0%. In the TLC, it will be really useful for both technology, charge current floating gate, because it can help significantly reduce the RBR from 12 to 0.5 and from 5% to 0.8%. So this it's applicable in 3D NAND flash.
Where's the no data for the last?
So some chips have some issue in the sense that if you program all the blocks, you cannot successfully sanitize the other pages. So I think that one you might need to talk to the manufacturer. Yes. Also, I'm not 100% sure if it's also related 164 layer, like not so many layers, and they come to the end. And then to conclude this topic, we perform all zero sanitization on 3D NAND, SLC mode, and TLC mode. Even though we can achieve 100% sanitization, but still there will be some disturbance happen in the floating gate NAND, and we propose the pulse low partial update for low disturbance sanitization engine to lower down the RBER, and we found out that at least in the SLC floating gate, the RBER is close to 0, but in the TLC, it significantly dropped the median RBER.
So one more question. So with the impact of aging and on the effectiveness of this, or the conclusions that you have on an older chip, would be interesting to get some idea about that. And also with these older chips, when you do this sort of sanitization, have you actually sanitized that page? Because there are remnants of data, right? That
I think it depends on how secure you want the old data. The old data you want. For example, in this Tesla image, it may not go 100% on zero sanitization, but then it's not visible.
No, I know. So even if you sort of are able to put 90% sanitization in a particular page, suppose, right? However, if that particular page had some, what I'm talking about, some data that's been sitting there for years, right? There is going to be some change in the profiles of the cells. So even if you put this sort of a sanitization, you can still kind of
see the remnants,
that profile, right?
If you give the chip to me, I can see.
So that's what I think topic 2 is.
Yeah.
Oh.
Yeah. So, okay. You should just
yes.
I'm solving it myself.
Yeah.
He's putting the story for you, right?
Okay.
Preparing the stage. So
Thank
now this
you.
is the second question.
Let's move to the fun part. So this is the ongoing work. Even though you delete your SSD and you think that, oh, this is everything got removed it and give the SSD to someone else, to your friend, or resell it, I still can recover some of your old informations. And this is the problem statement. The block erase is not enough for SSD. At the end of life, we still can extract previously stored information. Even though you perform block erase operation, I still can see some remnants out of it. And in this work, I will propose the method how to recover the informations, and the preliminary result is on the 64-layer 3D NAND, and we did see some traces of the previously stored information before the block erase.
So since you're switching the topic, so earlier you talked about override, all zero override. Now we are saying block erase.
Mhm.
How they are different?
All-zero override, pushing all the cells into the program states. Block erase is making everything back to the original factory, all one to the erase state. So it's the factory like states when you get
This
the
is
cells.
technically, but if you want to say it more, say someone who doesn't know, say much of zeros and ones, right? So which is more secure? Or what is the block erase is the last line of defense, right? Or this is the most secure mechanism to sanitize a drive, and this is happening in a entire drive scale. So before you discard your electronics, you issue this block erase command, and everything will be all one. So that's the block erase. And you are saying that even that mechanism is not enough.
Yes,
So
yes.
that's a huge step.
And then
Sorry, to add to that, I mean, also the in-place sanitization that you just talked about, aren't the techniques you're going to talk about applicable to that, to recover data from those stages?
and the higher P cycle. I think so.
Yeah.
I haven't tried, but I think
Okay.
we can. Yeah.
Because I think it should, right? It's the same idea.
Yes.
Right.
Before I move into the how I would recover the data, let's take a look at the life cycle of flash-based SSD and the data risk. Let's say you walk to the store and then you buy the SSD. This is the cells that you would get nice, fleshly, and clean. And as we perform program and erase cycle by putting information in, delete it, put more information, that will cause the defects in the oxide layer. And I use the black dash to represent the defects in the oxide layer. And as we keep using it, the defects will be even more like high dense defects. And at this point, this cell will be, I don't want to use the word bad, but it's gonna struggle to retain the information because electron will get trapped in the trap states instead of staying at the storage layer. So at this point, some people would just delete the drive and sell it on eBay without knowing that their previous information can be leaked. And this is when our data recovery process come in. And let's take a look at the physics, the cartoons explaining and actually what happening during the end of life block erase and data recovery. Let's say when the chip's close to the end of life and you want to put image into the chip, and because Tesla image has 0 and 1, so there are two possibilities of the cells going to be either in the erase state, the top row, or the program state on the bottom row. And because of the close to the end of life, there will be high defects in the oxide layer. This will cause the trap states. The electron will be trapped in the trap states. Then during the when you leave the drive for a long time without touching it, there will be some printing going on, meaning that some electron will get leaked, some will get repair the bond. So at the end, when you erase and look at these two cells, there will be significantly different in terms of the density, the oxide defects density. The top cell erase cells is going to have more of the defects, and the previously programmed cells will have less defects because electron repair during the retention. At this point, the controller cannot tell the difference between these two cells. And if we plot the image, if we plot the image, it's going to be all white. And if we read the page, the data page is going to be all one. So this is when our data recovery come in because we know that these two cells have different density, trap density. So first, I will start program both two cells with all zero pattern. And here I use 5 electron as a baseline. And if you can see on the top row, higher dense flash electron will get trapped compared to the lower dense, the previously programmed cells. Maybe just 1 or 2 electrons will get trapped there. And these two, if we read with the controller, there is no significant difference. They will see that both cells have 5 electrons, but the location of the electrons are different. So through times, if you let the data retention happen, the top cells, previously erased cells, will lose charge faster. And now, at one point, we will be able to distinguish between these two cells, the previously erased cell and previously programmed cells, by the amount of electrons stored in the storage layer. And this is how we distinguish between these two cells. So because previously erased cell will have less electron, so the distribution will be mostly on the left, and previously programmed cells will have higher electron. Distribution will tend to be more on the right. So if you apply read reference voltage, the default read, you might see some remnants, but because we have only one single read reference voltage default read, sometimes it's difficult to get the optimal point, the optimal between the separation between these two groups. There are multiple, since chips allow us to sweep the read reference voltage, I can sweep from the lowest VREF lowest to the VREF highest, and at this point I can identify the optimal separation between these two groups. And when I reconstruct the image again, I got something that looked like this picture that I stored previously.
So isn't there like a assumption here that you will have these two distributions at the end of life or whatever in the age two, right? So which could be the case if you've primarily just been storing zeros in some cells and primarily ones in some cells, right? However, in the presence of randomizers and also in the presence of other mechanisms that are in the FTL, where in order to prevent retention loss, over time, they also kind of have mechanisms to compensate, right? So do you think that these distributions would exist in real chips that have been aged with real use case patterns?
For Pasricha, there is a case that I try 7 days at room temperature. I still can extract. So it's not as clear as this one, of course, but I still can see some remnants of Tesla image. So I think it's.
I don't disagree that you will have some difference. And my question is like, how much of a difference, right? So if there is a significant difference, that's when you can kind of easily extract information. If not, then you can get maybe 5% of the 10% of the useful information that was there. Right? So that's the key question, right? So, but okay.
This imprinting, right? You need some amount of time. The data should be there. Otherwise, this repairing, right, of defects will not take place. So that's one important criteria, that you have to hold data for a certain amount of time to have this imprinting effect. And after that, you can recover based on the imprinting part.
All right, let's summarize the data recovery process. When we program R0, the distribution is barely distinguishable, so it's very close together, previously programmed and previously stored, previously erased cells. But once we let the retention mechanism happen a little bit, here later on, I will put the chip at the recovery temperature for a certain period of time to see this to see the separation between these two cells. And of course, with previously erased cells will lose charge faster because of the higher defects in the oxide layer. And then to get the optimal recovery, I applied adjusted read reference voltage to get the optimal point. And let's take a look at the experimental flow and results, and then conclude the talk. In my experimental section, I break it down to 3 parts: cycling, data imprinting, and recovery. Cycling, it's basically mimic the real world of using the chips, program and erase cycle multiple times, and then check the rated endurance on the data sheets and make sure that we reach that point. And then I erase and reprogram again with Tesla image. So this part will be the imprinting part. So theoretically, you should leave the chip at room temperature for a long time, like 1 month, maybe 1 week. But I just want to accelerate the retention loss and all of the mechanism. So I put the chip at too high temperature, 120 degrees Celsius for half an hour, and then perform block erase, do the R0 programming, and then keep monitor data retention. And this is the preliminary results that I got. Image on the top corner is the was it like a reference? This is the image I imprinted in. And then the left plot is the data leakage percentage versus the adjusted read reference voltage. As I sweeping the read reference voltage, at one point I will get into the optimize the point that where erase cells and program cells get separated. Not perfectly, but nice enough. And then when I replot the image from this point, this is what I got, the close to Tesla. And then if you keep continuously sweeping the reference voltage all the cells will fall below the read reference voltage and everything become white. This plot is to show you that this is the real data from real chips, to show you that the erased cells lose charge faster. So the distribution will be to the left more than the previously programmed cells. And because of the less electron in the floating gate, in the storage layer, the distribution will be more on the left. So 3000 PE cycle or Tesla image, the Tesla image is still can be extracted. And then I later let's try different temperature, 150 and 120 degrees Celsius recovery, because I don't want to wait for 1 hour to extract the information. So one thing I found is if you go with the high temp, 150 degrees Celsius, 10 minutes, you get almost 70% of the data recovery, but then it's saturated. So the longer you bake, you don't get anything much out of it. But if you drop the recovery temp down to 120 degrees Celsius, even though at the beginning you might not reach 70%, but the recovery, the data leakage can be higher and higher and higher, which means if I drop the recovery temp down to 65 and wait for 1 week, the data leakage can be higher than 70% maybe, or maybe 80%.
You can try that. You can stop at 60.
Yes. And then this is the data leakage percentage versus the recovery times under different P cycle. This is to show you all that the more you use the drive, the more visible Tesla image is, meaning that it's proof that it's something related to the oxide effects that get imprinted, your information get imprinted. And then
would the location of the block matter? Like in a 3D structure, would this be sort of recovery from a block in the middle layers versus would that matter or not?
that would be matter, because the middle layer might be more of the vulnerable. But
So it will be more susceptible to extracting.
Yes. But this one is on the bottom layer.
Okay.
Yes.
Is P like how many times you write in each one?
Yes. And then we are still working on this work, erase before data recovery process. But these are the publications that I have along to prove the physics that if you make the cells reach the end of lifetime, you anneal it, you repair the broken bond. The data retention property of the cells that was annealed in the program state will be better than the cells that was annealed in the erase states. So this is just like a physics on the building the imprinting part. And yes, there are some questions that I want to answer moving forward. For example, if we leave the chip at room temperature, would we still recover some data, and for how long? And then whether or not this technique work in different technologies, and what layer would be the most vulnerable to the data leakage, and then can I recover image or data from different types of storage, MLC, SL, or TLC, and then would the data pattern be different? Would make things different, yes. And then to conclude this chapter, propose the data recovery after block erase, and I found around 70% of the data leakage. And for today's talks, it's covered 2 topics: all-zero overwrite and block erase. The all-zero overwrite basically firstly evaluate on 3D NAND, and then propose solution because of 3D structure disturbance. And then for the block erase operation, we propose the mechanism to recover the information even after block erase. And yes, this is my publications. And then